Hey guys, so my name is Alex Suarez and I have the privilege of introducing Professor Dan Lloyd. So Professor Lloyd received his bachelor's from Oberlin College and his PhD from Columbia University. He's currently the Brownell Professor of Philosophy here at Trinity, and he has been the recipient of the Arthur Hughes Award for Teaching Excellence and the Trustee Award for Faculty Excellence. Professor Lloyd's scholarship is widely recognized. As a member of the philosophy department, he has published in the top journals of fields like neuroscience, psychology, and philosophy. Moreover, his work has won many accolades in these journals, such as the award he received from the Journal of Cognitive Neuroscience. He was also the recipient of a Fulbright Fellowship to Helsinki. In addition to these things, Dan has also published 2 books. The second of his books is a murder mystery and a theoretical explanation of human consciousness. And this book actually was reviewed in the New York Times and received Best Book of the Year from Forward magazine. Along with this, Professor Lloyd's research using musical tone, which he will talk about, using musical tone to interpret functioning using musical tone to interpret functioning magnetic resonance imaging data has been made into a multimedia music, film, and science exhibit. As a student, I can personally attest to Dr. Lloyd's skills as an effective professor. He provides his students with lots of guidance, and he absolutely values the inputs and opinions of his students in the class. He also has this exceptional quality of keeping all of his students engaged the entire time, something which I completely admire in a professor. So in sum, Dr. Lloyd is actually super duper cool. Without further ado, please help me welcome him to join the podium.
Thank you very much, Alex. I don't care about all that stuff except for being super duper cool. That's really quite wonderful. Thanks a lot. I want to begin by mentioning a book that you may know about by Daniel Levitin called This Is Your Brain on Music, based on a slogan that goes way back, This Is Your Brain on Drugs. I mention it because I want to distinguish what I'm going to talk about today from this book. This book describes how people respond to music, how music is produced, how the parts of the brain are involved in music as an external stimulus. I'm going to be talking about something quite different from that. I'm going to be looking at the brain and asking the question how it works to propose a fairly radical hypothesis that everything that goes on in the brain can be interpreted as having musical form, as being music-like, or if you prefer, being music. And so that's not just about listening to music or producing music, it's about everything. It's about thinking silently and so forth. The idea is that what's going on inside, between areas of the brain, can be interpreted with musical tools, not just listening or producing music. So it's quite different from your brain on music. This is your brain as music. So it's a radical claim, and to indicate how radical it is, I'll open up with a little analogy. Suppose, as I'm sure you all have asked, how does Yik Yak really work? What goes on inside your phone when you're handling an app? And you might want to start out in a good empirical scientific way by, for example, cutting it in half and looking at the 2 hemispheres and seeing if you can detect differences in function that way, or you might be a little more careful in your anatomy, taking it apart that way. And eventually you would find smaller pieces that seem to be different and distinguishable. And if you continue to look and started probing around with electricity and so forth, you'd begin to discover all the connections among all the parts. And finally, you might get all the way down to understanding the flow of current through things like junctions, transistors, and so forth. With a lot of work, you could get to 2 levels of explanation. The first would be the behavior, how you upvote a yak, stuff like that, the psychology of the iPhone. But the other level would be way down at the level of the wires, transistors, circuits, and chips. We could argue that our knowledge of the brain is somewhat bifurcated in this same way. We actually have a lot of knowledge of the low levels, neurons and other cells in the brain, circuits among them, and some of their interactions at this low level, equivalent more or less to the transistors. We also have connections among areas that we look at, that we also have an increasing understanding of, This large project, the Connectome, is the equivalent of the Genome Project, which looks at how brain regions talk to one another, a very impressive project now involving thousands of subject samples. And so we have the high and the low level here. But there's a problem, which is, if we go back to our analogy, I think can be made clear, which is that between the two levels is this vast gulf. If you knew everything about what's going on in your iPhone at the level of the flow of electrons, you would die before you understood how even one pixel appears on the screen. There's too much going on. Billions or millions of components, billions of connections, and even if you had it all right, and you could say in some sense, I know how it works, you wouldn't be able to get outside of that knowledge in order to actually have a workable explanation of psychology. What's needed is a middle level, something that enables you to link this very low level stuff to this very high level of behavior. And in the computer case, in the iPhone case, there definitely is a middle level, as is the case with all computers. In fact, without the middle level, there wouldn't be computers, and that's the level of the programming languages. At the bottom is a simple language, a machine language, which is what determines how the electrons flow into basic components of the computer, registers and so forth, how memory is incremented and all that stuff. On the basis of this language, higher levels are constructed, and so you get all the way up to the app level, and the app can ultimately be decoded all the way down to this very basic language level, and this can now be interpreted as the flow of electrons. And so now we have that middle level that goes between the very low level and the high level. And the only way we could ever understand a computer in its working is with something like the programming language level of explanation, in fact, several such languages. With that, we could say, oh, I do understand how the computer works if I know how to program it. Or if you're an engineer, I know how it works because I know how the register machines work and the basic CPU functions and so forth. And so with respect to this then, the assumption has been made that there must be something similar in the brain, that by analogy to computers, there has to be a programming language of the brain, something that works like the machine code or an intermediate level language like MATLAB or something like that in the brain. And this is a core hypothesis then of cognitive science, the computer analogy between computers and minds or computers and brains. Most explicitly proposed by Jerry Fodor in a book called The Language of Thought, proposing that there is a language of thought and that it's a kind of code, and it's a linguistic code, a language-like code, called, lightheartedly, mentalese. And the brain speaks mentalese to itself. Mentalese is not connected to any natural language, any surface language that we actually speak to one another. But it has to be there, argues Fodor, because otherwise we couldn't do what we do in terms of interacting with the world, in terms of our behavior. This is where my dispute arises, and where my proposal is at odds. I'm proposing instead the music of thought hypothesis, or MOTH, to answer the WOTH, and that the code, if you want to use it such, is comprised of musical relations and musical constraints. And so you could put this lots of different ways. You can say that that middle level is music-like, but if you're going to go with Fodor and say that the middle level is a language, I'm going to say that the middle level is music. It's not an audible music, nor is it an audible or readable language. It's a model, a conjecture. How are we going to ever assess that question between language-like and music-like in a system that we know nothing about, as if we were opening up the iPhone and ripping it apart and laying it all on the workbench? We have no idea what that language or code or internal system of operational rules, we have no idea what that is. So to get at that, here's a sort of thought experiment, which is, suppose we receive a signal from a distant planet. We know it's not natural, we know it's not random. We think they're trying to communicate with us. And so the question arises, is this a language that they're sending to us? We can't link the bits of signal that we receive to anything in the world. If we hear, if they're talking about a table, we can't go look and see if there's a table there. All we have are the uninterpreted symbol tokens, We could say there are little pauses in the signal. We take each little brick of the signal out, and we make a list of those, and we see repetitions, and we see which are used more or less, and that's all we have. We can never connect to the planet itself. And then we ask the question, well, is that language or is that music? Not an unreasonable question as far as extraterrestrial intelligence goes, because if you think about the signals we send out, which have now reached about 110 light years in all directions, think of the radio, and that's the kinds of signals that are out there. It's as much music as it is language. How would you begin then, without knowing anything about what anything means, to decipher this? As it happens with language, there is a way in, and this is the way in we'll take for this talk. Here's a literary work, and the words as they occur have been ranked from the most used word, which is the, on down through the first, say, 20 or 30 words. And each one of these asterisks stands for 1,000 occurrences of the word. Of course, the word the is the most popular, it's not surprising. If you look down the side here, you might get a clue as to what famous literary work this is. You shout it out. It's Moby Dick, and the clue is there. The word whale is fairly high up on the list in this one work. But if we extend out from this to 1 million words found in Wikipedia, we find a distinctive curve, the curve that you see on here, where once again the word the is far and away the most popular. The next most popular word is half as popular. The next is 1/3 as popular. The next 1/4. And this pattern is fairly closely observed. The first most popular word, the first ranked word, is, we say, at whatever its frequency is, the number of occurrences. The second most is 1/2 or 1/2 that amount. The third most used word is 1/3 or 1/3 that amount. The fourth used word is 1/4 or 1/4 the frequency of the first most used. And this goes on and on and on. And it turns out that this is an incredibly regular feature of language. It was really brought forward by George Ziff, and so now you get to know about Ziff's law, which is one of the most interesting, I think, empirical regularities there is. The frequency, that's the number of occurrences, is inversely proportionate to the rank, to whether it's first, second, third, fourth, and so forth. Ziff's law holds for English. It holds for spoken English. It holds for written English. It holds for every other language on Earth that has been studied. Thousands of data sets have been put into Ziff's law, and they all follow this pattern. It holds for programming languages, for artificial languages. Follow this curve. As it happens, the curve is extremely regular. It's a power law, and it can be described by an exact equation. And language seems to follow this equation. Even ancient and uninterpreted languages follow Ziff's law. That is, they look at the symbols that no one has any idea what they know. They count them up in terms of occurrences, and we find this pattern. Whatever the occurrence of the first is, the second most popular is 1/2 of that. The third most popular is 1/3 of that, 1/4 of that, and going on. It's an idealization of language which is stunning to think about. Other phenomena follow Ziff's law, but the takeaway here, though, is that language does. And so we can measure our conformity to the Ziff curve, to the Ziff distribution, very easily. And so for the purposes of this study, that's what I've done. With 7 large samples of language, both written and spoken, which I hope you can read alongside here. It's English, French, Spanish, Finnish, and Chinese, including spoken samples of the 2 of them. By taking, these are large strings of symbols. I take chunks of them, of 225 symbols each, and measure the Ziff, how close it is to the Ziffy curve, and find that there's a good commonality among the languages that I've used for this study. It is very close to perfect Ziffiness. We're looking at the fraction of the ideal frequency that is mirrored by the actual frequencies observed in the sample that I've looked at. So what we have is something that it seems like languages seem to fall pretty well on this. Can we use this then to distinguish between language and music? So we take musical samples, and I took 194 from 6 different musical traditions, I'll tell you about in a minute, and used each note as if it were a word. So each note, each tone becomes a thing that we're going to count the frequency of occurrences as and see if it matches Zipf's law. And if we do that, we discover that it doesn't come so close. Now, we're still in heavy-duty Ziffy territory here. Things are pretty close to that ideal curve. But across the 6 traditions, so we have 3 folk traditions and 3 Western composers, we find a fair amount of overlap. It's a lot noisier than the language data. But the important thing is it's distinct from the language data, that there's a fair distinction between them. And so if on this planet we were given a signal stream and we didn't know whether it was language or music, we might be able to answer that question by doing this. So this is the mean. The little circles are the means, and the little triangles going out are the 95% confidence intervals. And so if 2 of these bow ties overlap, then we have 2 signals that are not statistically different. And so that's the way to interpret these bar graphs as we go. So now, okay, let's get the brain into the mix, and how are we going to do that? So I don't have a scanner. So as is the case in Blanche and Streetcar Named Desire, I have to rely on the kindness of strangers. And they are very kind indeed. And so I've been able to use data from the Institute of Living, 2 blocks from here, but also archived data that is freely available on the web. Now, a brain image is collected every 2 seconds or so in the standard fMRI scan. It consists of hundreds of thousands of pixels. And that's, to analyze each and every one of them separately is too much, at least for this laptop. What we do and what most do is a form of pre-processing, which is known as independent component analysis. The idea of independent component analysis, well, here's an analogy. Let's suppose that you're all part of a chorus, and so we've got sitting out there the sopranos and the altos and the basses, but you're not sitting with your section. So in one row we might have 1 of each. And I want to locate where all the sopranos are sitting. What independent component analysis does is that. It will find the sopranos and distinguish them from the altos. It does so because they're singing different melodies. They have different signal streams, and all the sopranos, since they're singing in unison, they become a component. So a component in the brain scan then is a distributed area or maybe a quite focal area in which all of the pixels in the image are becoming more or less intense together. They're coherent. They're in sync with each other. And that change in intensity can be tracked in a time series, a graph which says that as time passes, sometimes this distributed component is more active and sometimes less so, and so also with these others that have their own time series. And there are artifacts here which we can reject. The eyeballs are not of interest in this category, but ICA picks them up too because they're part of the fMRI signal. So one way to kind of conceptualize then how we interpret this is in this video, which if you look at it, you'll notice that these are, that the intensity of the images are changing slowly over time. And this, by the way, is in real time. This is an fMRI signal. For what it's worth, it's Daniel Dennett's brain. And so as you can see, at any moment, there is one of these. These are all different, same slice, but we've projected onto it different components, different independent components. Sopranos, altos, basses, tenors, and so forth. At each moment, there is one of these which is more intense. And that one will be the one we'll say, is the note being played or the word being spoken? So if we have 10 different options here, basically we're looking at a pattern of time where we say, well, this is number 3, then number 1, then number 2, and so forth. So what we have is a way of translating brain activity into the same sort of signal stream or symbol stream that we are dealing with respect to language and with music. Here it is in a static form, and so again we have the regions of the brain. Each one has a time series, which is a series of numbers. I have a feeling this is not legible at all. So but if we look just at the numbers, we can for each one assign which one has the strongest level of activity. If we've numbered these components arbitrarily, we get a stream of symbols. And now we have the thing we can combine with both music and text, which we do using exactly the same techniques that I've just talked about. In this case, with respect to 3 different samples of brains, 99 in total. Some of them doing nothing. That's called the rest state, also known as the default mode. It's what our brains do when we're not busy doing something else. Some of them are healthy patients doing a simple button pressing task in the scanner, and some of them are schizophrenia patients doing the same thing in the scanner. The takeaway is that the method brings the brains together and clearly locates them in a domain which is closer to music, not quite overlapping in this case, and quite distant from all the linguistic examples. So by this empirical measure, we have an empirical test which has indicated that the signal that we're receiving, interpreting in this way, is more like music than it is like language. Now, that's a good thing, but we can go on from there to begin to ask about larger scale structures in the signal. What we look at so far we could think of as first order symbols or first order structure. In other words, what's the basic vocabulary and how is that vocabulary used? But we can start talking about pairs as if these are super symbols. These are just another set of symbols of which we have a series of these. And we can do the same sort of analysis on this. Now we're moving from then, we might say, the vocabulary available and the way that vocabulary is used, the sheer frequency of use of words or notes, to the pairs that are allowed in the various systems. And so we're beginning to make a transition then from the basics of the system to the grammatical constraints, the syntax, which allows transitions from some states to others, but not, and excludes some as well. And we can go up in orders as we go. And if we do the second order now we're looking at pairs, sequential pairs in our inputs. We continue to find the separation between the language cases and the music and brain cases. In other words, the 2 categories, if they're summarized down here, are overlapping. At this point, this distinction is weakening, but it's still present. And in the really the almost the final data slide of the set, we can put the 2 variables that we've been looking at, the 2 orders of ziffiness, on a single graph to kind of get a map of the lay of the land of cognition and language and music together. We find language all jammed up in this corner, very close to ideal ziffiness. And then we have a fairly tight collection of the brain data, and those are all the diamonds. And then a fairly large scattering of the music data, some of it a lot like the brain data, some of it a little like the language data, a lot of it quite less ziffy than all of the above. Just to kind of condense this a little bit, if we look at the median points, the middle of each of these scatterings of data points, and if we zoom in about by a factor of 2, we could begin to make some finer grained distinctions among the data. Here the languages Finnish, as anyone who is a non-native speaker of English knows, is very different from, who's a non-native speaker of Finnish knows, is very different from the other languages, and the Finns say the same about English and Chinese and other languages. We have our brain data in this zone where HC is the healthy controls and SC are the schizophrenia patients. The subjects who are simply resting in the scanner are here. And then we have the central points of the various traditions, and there's interesting structure there, something that would be nice to look at if we had more time. An empirical result. And so we want to say, so what? We always want to say, so what? We might say, well, okay, so you've said something about the kind of language the brain uses. It has these properties which are different from natural languages or spoken languages. Big deal. It's still the language of thought. Nothing has changed. Or on the other hand, we might want to say that really these 2 are different. These are both very fuzzy domains. There are borderline cases of both language and music. That's why we got the fuzzy cloud here. I'd like to suggest that these are two rather different domains, and so now I'll say a few words about the difference between language and music. And there are really quite a number of differences. Music, I'll make this brief, music's organized around tones, around pitches, and maintaining strict pitch intervals, jumps in frequency, is essential to the interpretation and understanding of music. Language, on the other hand, is organized around all the other things that go into making a sound, namely what are collected as timbre. That's things like the attack, the consonantal that comes at the beginning of a language sound, the structure of the harmonics that go with vowels, say, stuff like that that isn't part of what we use to interpret music. We hear timbral differences in music, but to understand a piece of music as the music it is, we really just need the pitches. You can understand Beethoven's Fifth if it's on a synthesizer, for example. Timbre totally different, but as long as the pitches are there, we can basically pick it out. Music, as we know, is periodic and repetitive. That's why you're likely to tap your foot to music, but not likely to tap your foot to a soliloquy in Shakespeare. That's a non-periodic signal. Language enables us to refer specifically to things in the world. It has an external semantic reference. Its meanings are attached to stuff. We can talk about tables and cats and mats using language. Music doesn't work so well doing that. There's no way to get your orchestra to communicate the cat is on the mat, in spite of valiant efforts to do that. Music does have a very specific syntax. The grammatical rules of music are very specific, and we then are aware of musical structure in a very detailed way. You can tell when a wrong note is played. In the context of just about any musical work, we're all expert at this interpretation. So the semantics of music is a semantics that refers to other parts of the music. Think of a sonata. One part of it is a reference to the other part, and what we enjoy in music is the way the internal relationships work out. As I mentioned, music's very repetitive. We talked a bit about how there are fewer symbols. And before talking about this, briefly, the evolutionary story for the two domains might be very, very different. Language is clearly adaptive, and once a species has begun to use language, that's going to be selected because there's so much that can be done with language. Not so clear with music. Steven Pinker declared that music is auditory cheesecake, that it's something that falls out from our language abilities that has no evolutionary significance whatsoever. There's something to that, in that it's hard to say why a species would be adapted to have music. There are lots of hypotheses about this. The thing is, we can't imagine being human without language. Everything that we think of everything that would have been impossible for our species if we had never developed language. On the other hand, we can think of something that would be very human-like without music. It would not be fun, and some of us would be hard-pressed for jobs, and so, but it would be, but it could work. A species could go on without music. In a sense, the contrast between language and music is summarized on this slide. The repetition, the smaller vocabulary, the periodicity in all of this, and if you recognize the piece, it is Beethoven's Fifth Symphony and piano reduction. Now, let's generalize from here and talk about whether these kinds of distinctions, how they might apply when we think about the high level, the behavioral, and ultimately the level of consciousness itself. So here is a rendering by Nick Sousanis, a graphic novelist, or anyway, a graphic artist, of looking at the Mona Lisa. And what his graphic reminds us of is that we never see a whole scene. We only see little bits of it, and each of these squares is a part of the Mona Lisa that we can see in detail at any one time. And he goes on to depict this graphically. We take our first look at the left eye, and then we jump to the right, and I go up to the eyebrow. And the fixation, the point that we can actually see, is fairly narrow, and so we're moving among fixations. Then on the top line here, we have the way the eye moves. It jumps to the right in order to get to this position, jumps to the right, bumps up a little in order to get to the eyebrow, jumps right, bumps up, and comes down in order to get to Mona Lisa's nose. Mona Lisa, to see it then, is a sequence of fixations. And each fixation conveys detail, but no fixation shows the whole picture at any one time. And so Susanis goes on to lay this one out in beautiful detail. He's following on a classic study of eye movement. And now the thing to look at, though, is the pattern of what appears as the content of each of these fixations. And you ask yourself, is this language-like or music-like? And what we see are the very features we've been discussing with respect to music, the repetition, the rhythm, theme, and variations going throughout. We can continue to generalize condensing this somewhat. The basic structures of repetition and variation and our ability to keep straight the relationship among these parts, that is to say, to know that the nose and the eye are in this spatial relationship to each other, since we can't see them both at the same time in the Mona Lisa, and our ability to put those parts together and work through them to determine meaning, that Mona Lisa's in front of a background and things like that. All of these are things that have counterparts in music, and what's I think most useful takeaway is that we have words for them. Music gives us terms for understanding these things which are normally mere theoretical entities. There are rules in world music traditions that state how these parts are related to each other. There is a theory, a way of beginning to address them. And so one takeaway is that we could use this form of interpretation as an addition to the toolbox of cognitive neuroscience. I'm going to take it, though, in a slightly other direction, and for the last way station in this talk. Music, sound, immediately comes to mind that since we're very good with sound and music, maybe we can exploit our abilities to discriminate musical sounds in order to begin to interpret the brain data, which I have argued is musical in its structure. There are many examples of this. A stethoscope, for example, is a case of converting a physiological activity into sound, of course. And a trained doctor can detect, say, if you have a bad heart valve or something like that, just by hearing. Could we do something like this, a brain stethoscope, with respect to the music of thought? And to do this, then, we're going to look at a case study. You all have a handout which will become relevant in just a second, a single page. This was based on work that was actually done by a member of the class of '07 who did her thesis work, actually it was a sophomore project work over at the Institute of Living, and published in a great journal in her senior year. This was looking at, and this is the source of the data we analyzed earlier of the schizophrenia patients and the healthy patients. And we have to sonify. You can put the stethoscope up to the head and nothing will come through. And so we have to do something in order to convert it into sound. And there's lots of different ways to do this. This is called sonification. It's the analog to visualization, turning data into sound. Any data can do this, so there's nothing particularly demanding about making it musical-based data, but we'll see how that plays. The method, and I'm going to blip over this pretty fast, is you give each region of the brain a tone, and then, as we saw earlier, what we have are these activity levels that are changing all the time. So you make the tone we assign to, say, region 1 will be, say, G, and we'll make that louder or softer as that region is more active. And another region of the brain, we'll call that C, that's active with a different time series, and so these will be becoming active and less active in a pattern, which we can hear. Finding that tone, finding those frequencies, we can do lots of different ways. The takeaway is that the tone and loudness differences that you hear are driven by the underlying data. That is what the fMRI machine measures. And so then, in effort to see if we can get a brain stethoscope going, we can convert the brain scans of both patients and healthy controls into sound. And what I put up here, and the colors are what are called sonograms, which you'll see are actually sort of like the score. They show the intensity of frequencies from the low and the lower left of the sonogram, from the low frequencies to the higher frequencies, and the sound will go across this. So it's a kind of visual way of also depicting what you can hear. So what I'm going to do is give you a training session in listening to healthy and schizophrenia patients. And after that, then you will take the schizophrenia quiz. You will have been trained for a total of less than a minute, and so you should be highly skilled in this activity. And I believe there's still a few of these handouts floating around. I'm not sure I made quite enough. So let's listen to one, and hopefully this will play. That's a healthy subject, just so you know. Each of these is 30 seconds long. And then this is a patient. Is the loudness good for the back, or do we need to crank it up a little? Up a little? Sean, can we increase the volume just a bit? On the... Oh, it's good. Okay, never mind. I thought you were saying turn it up, turn it up. All right. All right, here's our second healthy control subject. Same experiment. And here's our second schizophrenia patient. Okay, so you've got the handout before you. I will ask you, if you'd like, this is totally optional, to do it. Now, if you do so, I hope you will be willing to hand it in at the end. I mean, I would like to collect all these at the end. It's not a scientific study, but it would be informally interesting to see how you do. So be honest in your self-assessment. I'll tell you the answers as we go. And there's a few questions about your musical background, which I think just would be interesting to correlate this. So, are you ready? Okay, that was enthusiastic. So, without knowing then, the question to you on question number 1 is, healthy or patient? Go ahead. In the interest of time, I'm going to truncate these a little so that we can get done by 1:10. I happen to have the answers here, which is good, because if I lost this, we would be doomed. Subject number 1 is a healthy control subject. Okay. On to question number 2. And here we go. All right, if you've got your answer down, subject number 2. a schizophrenia patient? So go ahead and don't change your answers, please, but do make a note of them so you can score yourself at the end. On to subject number 3. Subject number 3, what do you think? That's right, a patient, schizophrenia patient. Subject number 4. Subject number 4, shout it out. That's a healthy subject. Subject number 5. Number 5, what do you think? That's right, it's a patient, schizophrenia patient. On to number 6. All together? That's a patient, that's schizophrenia. Number 7. Number 7? Yeah, a healthy patient. Number 8. A healthy subject, I should say. Whoops. What do you think? As it happens, this is a healthy subject. We can come back to that possibly in a minute. Okay, just 2 more. Number 9? Number 9 is a patient, a schizophrenia subject. And number 10. I chose these randomly, by the way, out of the data set, as I think would be appropriate. All right, and this is our last example. All right, your call on this. That's a patient. Okay, I got 30 seconds more here. I just point out to you that you have had no medical training with respect to this whatsoever, that your training session was 30 seconds long. How many of you got 6 or more right? Right. Chance is 5, okay? So you're doing great. You have a future in the medical profession. And I just want to conclude then by saying that what I presented is evidence that you are music. I'd like to thank you all. And by the way, I have a handout which outlines details about the data, the empirical data that I looked at in case you're interested in following up on that. I have lots of thanks to give here, including to a whole bunch of Trinity students over the years who have been part of these and related projects. And you can read more about it in just by Googling up the titles that you see on screen. And that's it. Thank you very much for your attention and patience.